Welcome back to this video series where we continue to talk about content in the book Introduction to Nonlinear Control. And in particular, in this video, I'm going to talk about content in chapter 11, giving some initial ideas about adaptive controller designs. And I want to start with a simpler example of an adaptive controller design for a very specific dynamical system. But the general setting we are considering here is a nonlinear dynamical system, x dot is equal to f of x comma u, with an additional parameter theta, and that parameter is assumed to be constant but unknown. And here we are interested in global stabilization of the origin despite the unknown parameter theta. So if we now look at the specific example, really a simple dynamical system, x dot is equal to theta times x plus u. As a reminder, we don't know the parameter theta. If we would know theta, then it would really be simple to come up with a stabilizing controller. But if we don't know theta, we can essentially do the same steps as we would to stabilize a linear system. So define u is equal to minus kx, plug that into our system dynamics to obtain the closed loop dynamics here, and we can conclude simply by looking at the sign here in front of x under which condition the origin is globally asymptotically stable, meaning for k minus theta bigger than 0 we get asymptotic stability, and for k minus theta less than 0 we have an unstable origin. So that would work if we would know a bound on theta, but if a bound on theta is unknown, well, then we need to come up with a different idea. Another idea would be to take a nonlinear controller, so simply adding an additional term, an additional degree of freedom, so adding minus k2 times x cubed. We plug that in again, end up with another closed loop system, now a nonlinear closed loop system, and we can analyze the equilibria and the stability properties of the equilibria. Here in this case, again, if theta is less or equal to k1, then we have a unique equilibrium. But if theta is bigger than k1, then simple calculations here tell us that we have 3 equilibria, which can be characterized here through this set on the right-hand side. To analyze the stability properties of the origin now, we can consider this Lyapunov-like function, or candidate Lyapunov function. V of x is equal to 1 over 2 x squared. We can calculate the derivative along solutions, and we end up with this inequality here, where we have these two good terms which are negative, but then we also have this additional positive term theta squared here. But it can be shown in this case that x of t for all t are going to converge to this set S theta, depending now on the unknown parameter theta and the constant k1. In particular, if we choose k1 larger and larger, then this neighborhood around the origin is going to get smaller and smaller. So with this, with these two controller designs here, what we can conclude is that a simple linear controller is sufficient if we know a bound on theta. If we don't know, if we don't know a bound on theta, a nonlinear controller would guarantee us convergence to a neighborhood around 0. But both of these approaches, at least these particular approaches here, would not guarantee asymptotic stability of the origin if we really don't know a bound on theta, so we need to come up with a different approach. And another extension, which we haven't discussed yet, would be the use of a dynamic controller. And this dynamic controller is a simple example now of an adaptive controller, which will actually allow us to stabilize the origin of our system here through a dynamic controller using an adaptive controller design. What is the main idea here? Well, as I've said, instead of taking a static controller, now we add dynamics to our controller. So we have, again, K1 as our degree of freedom, but then we have essentially another component, Xi here, which evolves according to the dynamics Xi dot is equal to X squared. To analyze the properties of the overall dynamical system, we can again look at the closed loop dynamics, which now are two-dimensional because we have the additional state of the controller. We can write that in terms of the second component in terms of aerodynamics. Here, by looking at theta hat as psi minus theta, so that's kind of the idea of this second component here, to estimate the unknown parameter theta through psi. Well, if we take the derivative here, we get theta hat dot is equal to psi dot, and since theta is assumed to be constant, the derivative is 0, which means we have theta hat dot is equal to psi dot is equal to X squared. Okay, well, how do we analyze the properties of the origin of this dynamical system here? Well, we can again come up with a candidate Lyapunov function and have a look which properties the derivative of the Lyapunov function satisfied, or candidate Lyapunov function satisfies. And here we end up with the equation v dot is equal to minus k1 times x squared. This means we cannot really conclude asymptotic stability of our overall closed loop system dynamics here. However, by using the so-called Lazal-Yoshizawa theorem, we can conclude that x of t, so the component x, converges to 0, even though psi might not converge to 0. But we only after the stabilization of the origin of our plant here, so convergence of psi of t to theta is not necessary in our context. And with this, this is a simple example showing some limitations or indicating some limitations of linear and nonlinear controller designs when they don't have a dynamic. And here we could see that with a simple example that at least for this particular example, the dynamic controller allows us to overcome some limitations and guarantee global asymptotic stability of the origin of our dynamical system. So these ideas can be extended to more complicated settings, and the main idea really would be to consider dynamic controller designs instead of static controller designs. I want to go to two extensions or generalizations here. One would be on general linear systems, where we are going to look at the idea of model reference adaptive control, where we consider to have a system x dot is equal to ax plus bu, where we have unknown matrices A and B, or at least they are partially unknown, so some components of these matrices might be unknown. And here then the idea or the goal is to set up a corresponding reference system where we have X bar, A bar, and B bar, and a corresponding constant reference input UE, where here we have three design parameters, namely A bar, B bar, and UE. And we can observe that if A bar is Hurwitz, which we can ensure by design, then UE implicitly defines an asymptotically stable equilibrium, meaning X bar is defined through the inverse of A and B and UE. So with these considerations, what we want to do is we want to design a control law. Now U being a function of parameters theta and two components, one with the reference input UE multiplied with the matrix M and a matrix L, also depending on the parameter theta and depending on X. And we want to design these matrices M and L such that we can look at the closed loop dynamics. So if we plug that in and make here these simple calculations, we end up with the closed loop dynamics, simply a linear system again, where we now have these matrices ACL and BCL, but depending on these unknown components A and B. So we want that our system here behaves essentially like this system over here. As mentioned before, there are compatibility conditions which need to be satisfied so that this is possible, meaning our B times L and B times M need to satisfy these conditions, these conditions here. But if that is satisfied, well, then we can again analyze the overall dynamical system here, now written in terms of the actual state of the plant, the dynamics of our controller, where we want our system to behave in that particular way. And then again, we have this dynamic component here, so a theta dot. So that's then a design a function which we can design in a particular way, such that hopefully we are able to select L theta or M theta in a way such that x of t converges to x bar. And under certain conditions that's possible, and possible in a constructive way, where again then we have this our dynamics in terms of the actual system of interest, and then our dynamic the dynamics corresponding to our controller in the second and third component here. For nonlinear systems, one can look at systems in a very specific form, extending the ideas of backstepping. Namely, one can look at systems in strict parametric strict feedback form, where we have already seen strict feedback form, where we had x1 dot is equal to x2, x2 dot is equal to x3, and so on until xn dot. Where then the input appears. Now we can additionally allow these additional terms here and functions phi depending on x1, x2, and an unknown parameter theta. If the system is in this form, then we can extend the ideas of backstepping as mentioned before. We get this horrible looking theorem here, but essentially the idea is to construct or look at aerodynamics and construct iteratively the dynamics of the overall system until we end up with the last equation where we then have control over the input, whereas before, again, we look at the virtual inputs and the corresponding aerodynamics to achieve certain closed loop properties. And the closed loop properties here are of the form that we then can guarantee that the first component x1 converges to 0, while the other components converge to equilibria potentially unequal to 0, characterized through the unknown parameter theta and these functions phi I. Well, I don't want to go into detail with respect to this theorem, and it's worth actually going through an example partially by hand, partially with the help of some corresponding software to see the structure of the construction here. With this, I want to conclude this video on adaptive control, and then in the next video we are going to continue with introduction to differential geometric methods, capturing content in chapter 12.